Okay, for Module 16b, we're going to continue talking about correlation, but we're going to talk about some of the caveats, some of the things you have to watch out for when doing the correlation, and how to handle situations where your data violates some of the assumptions of correlation. So your book has a nice discussion of this issue. This is a figure taken from the book of the fact that correlation is very dependent on the scale of the variables. So here we have a full data set, and it seems like there's a good linear relationship here. But if we were to just have a subset of the data, like only in a small range from 0 to 2, there does still seem to be a bit of a trend, but you would get a much lower correlation coefficient. Remember the correlation coefficient, I say lower, I mean lower in magnitude. So here it's negative 0.77, so it seems like a strong linear association. It's close to a magnitude of 1, and here it's much lower, 0.26. Remember, the correlation coefficient is not estimating the slope, so it's not estimating something intrinsic about the relationship between the variables. It's a sort of weird summary statistic in that it's capturing, it's more like a test statistic. It's capturing the degree of linear association. So if you have richer data from a wider range, you can get stronger evidence of a linear relationship compared to a smaller data set like this, where it's harder to detect that. So obviously, you can't always control the size of your data set and the range of values that are found in your study, but it's important to realize this, particularly if you're comparing correlation coefficients. Really, comparing coefficients around variables that have different magnitudes is really probably something you shouldn't do, because it's a very scale dependent analysis. So that doesn't mean it's not valid. It just means it's picking up on something that is dependent on the strength of evidence, which, having a larger range of values on the x-axis allows you to pick up more of an association than if you look at just zoom in on a smaller range of values. Okay, so that's one important caveat and how to interpret correlation coefficients. Remember, we talked in the last video about some assumptions of correlation. This is just a repeat slide from that video. So it assumes that you've randomly selected pairs of points from a population. So the random sampling assumption, that's assumption of pretty much all the tests that we do in this course. And specifically in correlation, we're assuming that both x and y are distributed as bivariate normal distribution. So any relationships between them is just a linear relationship, not any kind of curve or anything like that, or complicated. The scatter plot should look roughly like a cloud, is what we're saying by this, and circle or elliptical. And if you look at either one of the variables, they should look normal. So if all three of those conditions apply, then you should be in pretty good shape. And you can obviously do some statistical tests to look at this, but we don't focus on those details in this course. So here's an example of a bivariate normal. This is a scatter plot of x and y. And you see it seems to follow along a line, and it's roughly an elliptical shape here. So this seems like it's a good candidate for regression. It seems like there's a lot of points in the middle. So if we were to think about what the distribution of x is, it looks like it kind of goes up like that, and there's not a huge number of outliers. And on the y dimension, it's also pretty low probability and then higher here. I didn't do a great job of sketching that, but the point is they both look plausibly normal. This is over here on the left side of the figure is a depiction of a bivariate normal distribution. That's the theoretical distribution of a bivariate normal. So bivariate, remember, just means two variables, and they're normal in both directions. And so in this case, the axis that's kind of heading up is the probability density. So that's a joint distribution of two continuous variables. And so it looks like this nice hill that any way you look at it from any side, it looks like a normal distribution. So that's what the assumptions behind the critical values for the correlation table based on the t statistic. Those all assume that we have this bivariate normal. So if your data doesn't look like this, then you're violating the assumptions. You can run a test and get a p-value, but it really doesn't mean what you might think it means if you're violating those assumptions. So your book has several examples of situations that can deviate from them and things that you can look for in the scatter plots. Scatter plots are really useful for looking for deviations from the assumptions of regression. So here's one where in this direction, in the y direction, it looks like the points are more common right around the middle here. There's a lot of them. And, maybe there's a hint of that. Maybe it's a little higher, a little bit of skew in the x direction, but it looks pretty good. But we're violating that assumption of ellipsis. This looks, an ellipsis. This looks more like a funnel, right? There's very little variation on one side, and there's huge variation on the other side. So once again, you could calculate a correlation coefficient, but it's kind of a meaningless analysis if you're violating the assumptions. And so this would be a case when you probably shouldn't run a linear correlation. And here's an example in the second figure where an outlier strongly affects things. So if you were to run a correlation coefficient on this data set, it would pick up this linear trend here that's going through this cloud of points and this outlier point. But if you imagine dropping that outlier point and looking just at these points, there's almost no correlation at all. Maybe a slightly negative correlation, probably not a significant correlation. So regression is really sensitive to outliers. If we looked at what this data would look like on the x-axis, sort of sketch the distribution there, it looks kind of normalish there, but then there's this hump for this one data point. And similarly on the y-axis, there would be the hump associated with that outlier. So that's another case when we shouldn't do a regression. And then here's a case where there does seem to be a relationship between these variables, but it doesn't seem to be a linear one. It's not a straight line. So once again, if we did a correlation, it would pick up probably on some kind of line like that through the data set. You might get a significant value, but it's really not a meaningful value that you should interpret. And so make sure to check the assumptions. Okay, so what are your options if you're in one of these situations where the data don't appear to be matching the assumptions of correlation, so you don't want to just do a correlation analysis? Well, one thing you can do is just look into transformations of the data, much like we did talking about t-tests before. The t-test also assumed normality of the data, so if you have data that didn't follow the normality assumptions, you could do transformations of those data points. So I simulated some data in R and just going to walk through some examples of what some different cases might look like. Here's a case where everything looks nice. There's a sort of elliptical cloud here of points, and if you look at the histogram along the x-axis, looks pretty good, looks pretty normal here, looks pretty normal on the y-axis. So we've got what appears to be a linear trend in the data. The data points fall in kind of a circle or an ellipse, and each of the values looks like a normal distribution when we look at just the value by itself. So we should be good to use a correlation there. So that's great. What about if you get something like this? Okay, well, here it looks like maybe there's some kind of association. There's higher values here than there are over here in terms of the y-axis. When the x is large, you also get large y values. But it doesn't seem to be linear. It seems to be some kind of curve maybe. The x-axis looks not so bad. It looks kind of like a normal. It's actually the same variable I showed on the previous slide. But what about the y-axis? What's going on here? This is really skewed on the y-axis, so it doesn't look anything like a normal distribution. So when we have right skew, I know it's weird to look at the plot being up, turned on its side. So up would be the right axis in this case. When we saw right skew before, we thought, well, maybe do a log transformation. So if you were to do a log transformation of this data, log transform the y values here. This is the original, and this is the log transformation of y. That's what it says here on this axis. And you can actually see that these points do match up. There's a point right here around 0 on the x-axis, and that's right there. All of these points match up, but notice how all of these points that are really large in the original data get scrunched down much closer to the body of the rest of the distribution. They're no longer outliers, and it really crunches down that right skewed tail in the y-axis. And so now this looks much better. And so now we can just proceed to say, okay, once I've done that transformation, I check, things look elliptical, things look normal on each of the axes, the association seems to be linear. I can do a correlation analysis on the transformed data. If you have something like this, well, what's going on here? The y-axis looks pretty good, but we have right skew now on the x-axis. Well, you can transform the x-axis. We didn't do that before when we were looking at two-sample t-test. We just had two categories then. We didn't have a numerical variable on the x-axis, but there's no reason you can't transform the x-axis. So here's the log transformation applied to the x-axis only and the original data on the y. And once again, all these points here that are trending really low get squished up, and you have a much more oval distribution, and it follows a linear association. So once again, it would pass all the tests. It looks like an ellipse. It's a linear association. The x looks normal. The y looks normal. So you're fine to do a correlation on that data set. What about this example? What do you think is going on here? You might pause and look at it. Well, it doesn't look like an ellipse. It doesn't even look like a linear association. There's a huge cluster of points right there, and then just a spread of points. and maybe some association. The high values of y tend to be pretty high values of x, but it's not a linear association. It's a hard to describe curve. It's sort of, I don't know how to describe it even, like a funnel on both axes. And if we look at the distribution of x and the distribution of y, we see skewed distributions towards the large side. So you can actually log transform both axes. So here's that data I just showed you. If we log transform x and log transform y, then we get our nice relationship again. So you can play around with these transformations. And in this case, once again, nice ellipse, linear association, looks like a normal for the x, looks like a normal for the y. So that transformation seems to work at giving us a data set where we can look for an association between variables. Now it's no longer a linear association between the raw variables, it's a linear association between their logarithms, but still we can report that in our conclusions. And we're doing a test now where regression is appropriate because it's meeting the assumptions of regression. So once again, if you've got deviations from the assumptions of correlation, what can you do? The first step you can do is think about transforming to achieve the bivariate normality to do a linear correlation. I often just call them correlations, but they're linear correlations. Remember, this is an important point. We don't just try a transformation. Sorry, there's an extra T here. We don't just try a transformation to get a small p-value. We're supposed to transform our variables and look to whether they fit the assumptions of the test. So we can try multiple transformations. We should go with the one that gives us the best fit for the assumptions of the test. And then we proceed with that transformed data to do our test just on that one transformation, not on every one to maximize our power and get a low p-value. Okay, so that's not a legitimate way to do science. Instead, we want to make sure that we're satisfying the assumptions of the test. Okay, and just as before, if we can't find a transformation that works, we had non-parametric approaches. There's a non-parametric approach for the correlation as well. It's called the Spearman's rank correlation. So in the Spearman's rank correlation, you assign ranks to the first variable, then you assign ranks to the second variable, and then you calculate the linear correlation test statistic. It's little r for the correlation coefficient, and we usually subscript it with S to indicate that it's a Spearman's correlation. And then we're going to look up that test statistic in a different table, a Spearman ranks table. If you have really large values of n, you can convert it to a t-statistic like we did before. But it does have a different null distribution for reasonable sizes of n. And I should have emphasized on the previous slide, we prefer to do the transformations first. That's our first choice. If we can get away with transforming the data, that's the better approach because that has more statistical power. Non-parametric approaches tend to lose statistical power, so we only do this if we can't find a compelling transformation. Or if we want to say, even making very few assumptions about the distribution of the data, we can still find a significant association. So these non-parametric tests make very few assumptions about the raw distribution. Okay, so I went through the procedure briefly. Let's walk through an example. I'm going to go back to the example that we saw with the data from the Vostok ice core on the carbon dioxide concentration at periods of time way in the past and the temperature anomaly. So this was the raw data. I mean, this doesn't look like it's necessarily, it's linear. I wouldn't necessarily call this a elliptical cloud. It's really hard when you have this high correlation to see if there's an ellipse. It doesn't look terribly non-normal to me, but you might be in a situation where you really want to say, okay, well, for the sake of argument, I want to use a test that makes very few assumptions so that it's robust, even if those assumptions are wrong. So I'm going to prefer a non-parametric test. That means I'm going to sacrifice some power, but hopefully have a more robust test result. All right, so how do we do the Spearman's rank correlation test? There's our raw data. We say, okay, we want to calculate the ranks for the carbon dioxide. And the way we do this is we just think about listing them from smallest to largest. Let's see, the smallest value in here is 180. That would be 190. So I'll put a little check mark here. That's 2. The next one is 200. That's 3. Let's see, it looks like 215 is the next ordered variable. That's 4. Let's see, 230. That's the 5th. And 250. That's the 6th. And then 280. But we've got a tie here in 280. So 280 would be the 7th, and 280 would be the 8th. We don't, 7th and 8th would be the raw rankings, but we don't know where to put the 7 and where to put the 8. So instead, we average those values and put 7.5 in both of those. So here's those ranks filled out. The ties here, we assign the same rank to them. So this is the ranking of just that one variable. Remember, you were going to rank one variable and then rank the next variable. We're not going to shuffle everything around. We want to keep the association of the raw data in the original pairs. So we don't like shuffle the whole table, but we do assign ranks for the carbon dioxide. And so now we're ready to rank based on the temperature. If we were going to write these down, excuse me, I went ahead too far. The lowest one is -8, so -8. And the next lowest one is also -8. So we have a tie right out of the gate, so 1 and 2. So they would get ranks of 1.5. Then we have -6, and we have that again, so -6, -6. So this would be 1, 2. This would be 3 and 4. The average of those would be 3.5. And then we have -3, -2, 1, and 2. So -3, -2, 1, and 2. Right. And so those ranks would be 5, 6, 7, 8. Okay, and that's what we've got assigned here. The lowest values were 8, 1.5 and 1.5. The next lowest were 3.5. So that's assigning the ranking based on each of the variables. And now we're ready to sort of throw away the original data and just concentrate on the ranks and do a correlation analysis on the rank variables as if that were our raw data. Okay, and this, if you think about it, the ranks aren't really normally distributed. They're kind of uniformly distributed. There's a rank of 1 and 2 and 3 and 4. There's just kind of an even distribution of those. So we're not quite fitting the assumptions of correlation. And the way that's going to reveal itself is that we're going to calculate a correlation coefficient, but we're going to look up the tail probability associated with that in a different table. So we do have to acknowledge that this is no longer fitting the assumptions of linear correlation, but the rank correlation is a valid way to analyze the data if you use the correct statistical table. Fortunately, we don't have to learn a whole new procedure for calculating the test statistic. Here's what the data looks like in terms of ranks. I should have put this up earlier. Here's the 1.5 and 1.5 tie, and here's the 3.5, 3.5 tie, and there's a tie in the other variable at 7.5 and a 7.5. But it looks a lot like the real data because there's such a strong correlation in the real data, and it really seems like there's a very strong correlation here too. A nice line fits most of those data points. Anyway, but that's what we're going to analyze. We're going to do a correlation coefficient on those. So how do we do a correlation coefficient? Well, first step is to average the x and average the y. It turns out that when you're doing the Spearman rank correlation, x bar equals y bar, and it equals n plus 1 divided by 2. That's just a property of the ranks. There were 8 data points, so n plus 1 is 9, divided by 2 is 4.5, and those sums of ranks are going to add up to that term in each case. So you can save yourself a little bit of time that way. The next step is to calculate the deviations from x and y. So 7.5 minus 4.5 gives us 3. 1 minus 4.5 gives us minus 3.4. Since there's the same means in both cases, we're really just shifting these values down by 4.5 in each case. So this is a transformation of the data into the deviations from their mean, right? So hopefully that makes sense. For instance, you can work through any of these you want. 7.5 minus 4.5 gives you 3, whereas this value is 7 minus 4.5 gives you 2.5. So those are the deviations, and that puts us in good position for calculating the rest of the work that we need for the correlation coefficient. We square the x deviations and we square the y deviations. Those are going to end up in our denominator. And we look at the sum of products. So 3 squared is 9, and negative 3 squared is also 9. There's a lot of repeated numbers in here. But we square, each of these values gets squared, and each of these values gets squared for the y squared values. So that's all that's going on here. We get all those squares. These are the sums of squares for x and y, and then we can sum them up. And we can also look at the cross product, right? So the cross product 3 times 3.5 is 10.5, and here's negative 3 times negative 3, that's also 10.5, etc. So this column here is just coming from the product of these two things. Those two combine to give us that column, and then we sum in all across all the data points to give us this, the sum of squares for x, the sum of squares for y, and the sum of products of 40.5. So this is our formula for the correlation coefficient, the Spearman correlation coefficient. It's exactly the same formula as it was for the correlation coefficient of linear correlation. All we're doing in Spearman's is we're just doing a linear correlation on the ranks instead of the raw data. So the sum of the products goes there in the numerator, and each of these is summed, and then we take the square root, and then we multiply it times the square root of the other one. So 40.5 times the square root of 51.5 and 41. The square root of 51.5 times the square root of 41. The square root of 41.5 times the square root of 41. Unsurprisingly, it's a number that's pretty close to halfway in between those values. And it's really close to 40.5. We get this really high correlation coefficient of 0.982. Okay, so when we're doing a linear correlation, we would convert that to a t-statistic and look at it in the t-table. But for the Spearman rank correlation, there's a separate distribution because really the inputs are not normally distributed. And so someone had to figure out what the null distribution for the rank correlation of ranks is. And so some statistician has done that. And so it turns out it's a table that instead of calling it degrees of freedom, they just call it n because we don't subtract anything. We just count up the number of pairs of data points. We had 8 in our example, so not that one, not that one, not that one. Here's the one we'd look at. Obviously, the real table is much larger. And so at the alpha 0.05 level, there's your critical value. You have to have a correlation of at least 0.762 in order to have a significant correlation. And at the 0.01 level, it's got to be a correlation of 0.881. So those are the critical values. It turns out that the correlation coefficient, which we can think of as a summary statistic, is the test statistic in this case. And so you see you need really large magnitudes. I should mention you're looking at the absolute value of the correlation coefficient. So if you have a negative rank correlation, you just throw away that negative sign and see how it compares to these critical values. So here's our summary statistic, our test statistic. It's the same in this case. And here are the critical values that we just looked up in the table at the 0.05 level with 8 data points and the 0.01 level with 8 data points. These are the critical values. Since our value is more extreme than the 0.01 level, we can say that the p-value is less than 0.01. So we might summarize that as we have a significant evidence, Spearman rank correlation. There's our test statistic, p-value, less than 0.01 from 8 I-score samples. So that's where we're telling people our sample size that there is a positive correlation between carbon dioxide concentration in the atmosphere and the temperature anomaly. See the figures, how we would normally describe this data, because there's a lot of summary statistics you could report, but figures are really great for showing the reader what's going on there. So hopefully that makes sense, and hopefully it also seems familiar. It's very similar to what we had done before in Chapter 13 when we had violation of assumptions. We can think about transforming the data so it's legitimate to do the test, and if that doesn't work, we can fall back to a very robust non-parametric approach. All right, that's it for this video.